thankful and honored to be presenting my work in front of this community. As you said, I'm starting my second year of PhD of the project entitled as the interface behavior, dynamic interface behavior of soil nailed walls at the RRO laboratory of the Gustave Eiffel University. Can we flip the slide? First of all, before beginning, let me give you a little brief of what the RRO laboratory is. It's mainly the risk, rocks, and geotechnical structures laboratory. It deals with the applied issues that are identified during real jobs and real on-site tests. The lab mainly focuses on two different scope of actions. The first is the observation and the monitoring of sites of and some geotechnical structures. The other is the study of the behavior, dimensioning, and the design of geotechnical structures. For that, the laboratory employs different methods of research, including experimental, mostly one-to-one scale, and much of the times, whenever possible, it's on-site tests. The other would be through analytical calculations, followed by some numerical modeling, focusing mainly on the usage of César SPC software. In recent time, many research are ongoing as instrumentation and monitoring of sites through optical fiber technologies, as behavior and diagnosis of masonry structures and other works that are being done recently. Can you flip this slide?
Yeah.
As for soil nailed walls, mainly we are focusing on the local behavior of soil nailed walls against seismic events. However, let me give a grand aspect about these structures. Soil nailed walls are soil retaining structures where the soil mass is being reinforced by sealed grouted steel bars. On the economical level, these structures are of quite reduced cost of construction, as well as rapid time consumption and easy implementation, even on small sites of excavation. When it comes to seismic events, their performance have proved to be quite excellent, as has been detected by surveys of post-earthquake events. The stability of the fundamental principle of stability of these structures lies in the interaction that occurs between the inserted inclusions and the soil mass itself. The predominant resistance is offered by the nails is due to the axial tension that develops inside these nails upon the deformations occurring in the soil mass. The highest tensile force is located at a point where the intersection of this point with the nails marks a potential failure surface, as you can see in a dotted red in the first figure, dividing the soil mass into two different zones: the active zone, where the frictional shear stress occurring is directed outward, and the passive/resistive zone, where the shear resistance is directed inward, and it is mainly the reason of stability and protecting these nails from being pull-outed. If this resistance provided by the passive zone is not sufficient enough, nails would be pulled out, aside with many other modes of failure, but we mainly focus on that in this study. So, by that, to summarize it in another ways, the displacement that occurs between the soil and the nail induces friction at the interface between the inclusion and the soil, which is the main reason of stability of these structures. When it comes to the seismic behavior, the current design methods do not take into account the complexity of the seismic load, along with ignoring the flexibility of these structures, which deal to an overestimation of the inertial forces that these structures are being subjected to. On the other hand, we have the nonlinear behavior of the interface between the nail and the soil, which is also mostly non-accounted for, leading to an underestimation for the resistance of these structures, both leading to an over-designed structure. However, in my research, if we can flip to the second slide, I would be mostly focusing on the nonlinear behavior occurring at the interface. To better understand that, we can move on. To better understand the problem, it's mainly how the friction occurring at the interface is resisting the tension occurring in the nails. In other words, it's a simple equilibrium problem. Combined with Hooke's law, allows us to write the friction coefficient tau x, as we previously said, which is the main aspect we're focusing on in terms of the displacement that are occurring at the interface. That is for a static problem. But as we see in the next slide, when it comes to dynamic problem, the acceleration occurring at the, in the case of seismic or dynamic loads, is to be accounted, turning the equation into what follows. What we don't know in that equation is what is tau x in case of dynamic events, and it's mainly influenced by different parameters of the load itself, including the frequency or the amplitude of excitation, going to the properties of the soil itself, not to mention also the confining pressure of the soil that which the nails are included in. So the following research will focus on understanding the local interface behavior between the soil and the nail, as well as identifying the parameters that influence the friction at this interface. How? Through different literature review and aspects, it has been agreed that pull-out tests are best to assess the interface behavior. In our case, it's dynamic pull-out test. For that purpose, if we can flip. For that purpose, the HAWWA laboratory at the Gustave Eiffel University have designed a new dynamic pull-out device. It's mainly a hydraulic circuit constituting of 5 different parts that are all of lightweight in order to be transmitted to perform site experiments at some advanced stages of this research. The main principle of functioning of this device is that it allows us to impose a static tension that is defined by its duration and its magnitude, as we can see in both figures, and to superimpose a vibrational pulse that is centered with a percentage of amplitude of this load itself. We can see that both configuration that can be used, the steps configuration in the first figure and the slope configuration in the other, and the vibrational pulse simultaneously applied to the load in order to mimic the dynamic load that can be subjected to. After different and many experiments we've done, I'm going to summarize the final experiment that has been done in this scope. In order to perform such tests to mimic the real cases, we first prepared a steel bar occupied with 2 optical fibers on its flat edges. The steel bar is of 3 meters of length, and double optical fiber has been attached to it in order to allow the monitoring of deformations all along the bar through the loading procedure. This steel bar was then inserted into a metallic tube of 150 millimeters in diameter, followed by insertion of the sand, which in this case, Houston sand HN31 was used. The sand was compacted into by the aid of a vibrational needle, and aside with the optical fibers that have been used in order to monitor deformations, displacement sensor and a load sensor were attached to the head of the actuator, as can be visible in the setup in the figure on the right. The following test was mainly focusing on studying what influence the frequency has on the friction occurring at the interface. For that purpose, we have varied the frequencies between 1 to 5 hertz. We chose to use a steps configuration. As you can see, this is the load profile that has been applied. The ranges of loads were between 15 to 188 kilonewtons, plus minus 5% of amplitude of the pulse itself. As I've mentioned, we have used double fiber this time. So one fiber is connected at the top of the steel bar. The other is connected at the bottom of it. So the measurements obtained, which is the strains all along the length of the nail for each of the steps. So we can see each one correspond to one of the steps. And in order to assess the values, we chose to use the average of these two measurements. If you focus on the figure showing the averages, where it measures the strains from the nail, where it is the first point of the optical fiber, it's the end of the nail, and its head, which is some point where the tensile force is applied, we can clearly see that these strains are increasing as we move from the nut, which is at the end of the nail, to the head where the tensile force is obvious. And this is also clear by the equations of that we can see in the following, which means the friction is increasing all along the length of the bar as we are loading. If we can move to the next slide, one can see that with the aid of the strains that we have computed and using the following equation, we computed the friction coefficient at each of the different frequencies of loads that we have applied. We can clearly see that as the frequency increases from 1 to 4, the friction coefficient is also increasing, clearly obvious in the first and the last step. However, as for the frequency of 5 Hertz, things change. We are still trying to figure out in more advanced testing how to check on that. If we move the slide now, we have realized that we need to increase the friction at the interface, and for that purposes, increasing the dimension of the inclusion would be applied, and as well as increasing the roughness at the interface in case of restrained dilatancy of the soil, as well as increasing the confinement of the sand that is used. This can be done by two different techniques, either by increasing the interface roughness through grouting the nail, which has eventually been executed in the lab. We already casted concrete of water cement ratio 0.45 in a tube and on the nail that we have been already using. At some stage now, we are going to stick some sand particles to that grout in order to ensure an increase of the roughness of the interface. The other solution that is related to the confinement pressure, if we can move a slide, would be either by using an elastic membrane that surrounds the soil and allow the flow of some fluids inside to increase the pressure on the sand, eventually the confinement pressure. This is still under study because we have realized that fluids may leak and eventually the pressure monitoring would be somehow challenging. The other solution that has also been proposed is to compress the tube itself, the metallic tube that we already mentioned, and by that also allowing us to change the confinement pressure. Both methods are still under study. None have been yet executed, but there are still suggestions for the upcoming work. And by that, we come to an end of the presentation. Thank you so much for your attention. And I'm ready for any of the questions you have.
Merci, Ghida. Thank you for your presentation.
Thank you.
Donc, est-ce qu'un participant a une question sur la présentation qui vient d'être réalisée?
I will ask a question to Ghida.
Yeah. Yes.
So I understand well that it is a real scale model that you have in the lab. It is at a real scale, not a small scale.
Yeah, it's not a model test. It's up to real scale. Yeah.
Okay. So what are the other limitations of your model tests?
We haven't done any model tests. As I've explained, we are dealing with the real size nails because at some point we decide also to test the following aspects at field testing also. But if you ask what are the limitations recently for the tests being done at lab with this configuration, is that the quantity of sand we are using recently is not up to the overburden pressure that we wish for. So that's what we are trying to work on to improve. That's the main issue at the moment.
Thank you, Ghida.
Thank you.
Ok. Donc, si nous n'avons plus de questions,